So this morning, I'm going to go into two things. The first one is more theoretical because I presented empirical evidence for the stochastic gradient. I gave some limited proofs in one dimension. But in fact, in the beginning, I made this point that you can use stochastic gradient for a lot of algorithms. And there are a lot of conditions, like partial non-differentiabilities or things like this. And what I would like to show is that even though the speed is difficult to estimate in many cases, you can establish the convergence in extremely mild conditions in very general setups. And there is a very well-oiled machinery to do that. I would like to go on that and show how it works and how you can do that, because a couple years ago there was a fashion that lots of papers came out about old algorithms with a kernel variant. It's about the same thing. You could have lots of papers about stochastic gradient with applied to X or Y or Z, and the fashion nowadays is that they want a convergence theorem. So they don't care that there are general ones. So I'll tell you how to do them. The second part is going to be about the imbalanced data set. So I prepared some slides yesterday, and I'm going to give an idea of what's there. So we have all these algorithms, and the little analysis I've shown works for differentiable case. When you have a nice Hessian, everything's fine. But for the perceptron already, you have a non-differentiability. Well, no? OK. No battery. So can you see the mouse? Yeah, you have this non-differentiability here, so this hinge point that's a bit annoying for gradient algorithms. For the lasso, you have either this hinge point in the regularization, or in this case, the projection operator. When you split it, you do the trick of splitting it in two. And for k-means, you have an argmin. So again, this is something where you have hinge between the various possibilities. So I'm going to first look at the convex case. And I'm going to present three proofs. And only the last one is about stochastic gradient, because I want to show that the complexity is not really in the stochastic part in that case. In the second part, I'll discuss the non-convex case. And the third part, the second-order methods. So let's just go. Notations. So the cos C of W is an expectation over the example Z of a loss L of Z and W. The stochastic gradient update is the same as usual, except that the notations are slightly different here. And the condition I'm going to want is that the expectation of the update factor, the J factor here, is the gradient of the cost itself. And I'm not saying that the J of ZT WT has to be the derivative of L. This implies that it's the derivative of L almost everywhere, but in some spots it could be different as long as the integral is satisfied. So in particular, if the loss function has a hinge, you can just skip that point and say J equals 0. It's not going to impact the expectation if these points are rare enough. And at some point, I'm going to talk about the Hessian, because I'm going to assume that the cost itself is continuous and nice. So the trick is to say you might have discontinuities or non-differentiabilities in the loss function. But when you smooth everything using the asymptotic probability, we assume things are smooth and neatly behaved. So basically, we use a loss that can have very pathological things. But pathological things are easy to implement, usually, like the perceptron, to optimize, on average, something that's smooth and well-behaved. So the convexity I'm going to work with is something, well, it's a form of quasi-convexity result. And I'm just going, the condition is going to be that the product of W minus W star times the gradient in W, the dot product, is greater than 0. That means that if I'm in, so these are level curves, if I'm somewhere here, the gradient of the cost takes me in the right direction. That the angle between the vector that goes from the current point to the solution and the gradient is small. It's less than 90 degrees. There is another little complexity here, this inf here. It means that, and this is going to remain true strongly enough until you come very close to the optimum. It's not a very strong condition. If you have normal convexity or strict convexity, it is going to be verified. It also means that the gradient doesn't vanish, that you have no flat zone. So for the learning rates, so the gamma t, we have the requirement that the gamma t times the update itself goes to 0. Otherwise, you're floating above the optimum, you're not going to converge. So, and you have two ways to enforce that. One is to have learning rates that decrease, and the other one is to have gradients, or I call that the gradients, even though they're not necessarily the gradients that decrease. Now, if you look at the expectation of this gradient squared, you can say, well, I'm going to develop it around the W star, and you find that often they satisfy a bound that has the form A plus B times the distance to the optimum squared. And if A is different from 0, that means that the variance of the gradient, yes?
What's the ZT vector?
ZT means example.
Oh.
It's the pair xt, yt. So yeah, it's convenient to do that because it makes less to write. So usually the A is not 0, meaning that when you're at the optimum, if you look at all the examples and take all the gradients for each of them, you don't have 0, except in very pathological cases. So because the A is not 0, the learning rates must decrease. So now I'm going to go through 3 convergence proofs. I'm going to start with something very simple, which is continuous gradient, continuous time. It's simple math. The second one is the batch gradient, where you'll see it's already more complicated. And the last one is the stochastic gradient, which is going to be a small extension at this point. So continuous gradient, continuous time, everything nice, nice functions. Basically, you want to have a W point that moves, and the derivative of W with respect to t is basically the opposite of the gradient. So that's the dynamic of something going down without damping, without inertia. So the first step for proving that this converges somewhere is to define a Lyapunov function. It's a big word. A Lyapunov function means something that's going to go to 0 if we reach the optimum. So it's a measure of how far you are from the optimum. And you can define several kinds of Lyapunov functions. You define something that's convenient. That's the idea. So once you have such a function, the only thing we have to do is that it goes to 0. The second step is to say that it converges somewhere. And you write its derivative, so dh over dt equal 2 times w minus w star dw over dt. dw over dt, you know it's a minus gradient. And you get just the general convexity argument. So basically, you know that dh over dt is less than 0, so h is decreasing. And you know that it's bounded from below because it's positive, it's a square. So therefore, it converges somewhere. Now we have to show that it converges to 0. So I write again dh over dt equal this thing, and I say it goes to 0. And because we had this, let's go back a little bit, this silly inf condition in the general convexity hypothesis, that means that if this goes to 0, w minus w star must also go to 0, because the only way this product can go to 0 is by becoming close to the optimum. So that's a consequence of a relatively strong convexity. Then you're done. So that's very simple. There is even no gain problem here. You don't have a gamma t. It's not necessary. You can put anything you want. It works. Well. So now let's look at the batch gradient. This time I say Wt plus 1 is Wt minus some learning rate and the gradient of the cost in W. Same thing. I define a Lyapunov sequence. It's not a function anymore. It's a sequence that's discrete. And I'm going to go through the same steps. But before, I'm going to go through a little lemma that's useful. We want to prove the convergence of a sequence, and I'm going to do it in a slightly indirect way. So you have a sequence, it does zigs and zags like this, and it's supposed to be positive. So at any moment, you can say that the value of the sequence is the sum of the zigs, the steps you do during the zigs, minus the sum of the zags. So let me say, this is a zig, this is a zag. So if you do the sum of the zigs, you have something that goes up, and the sum of the zags is something that goes down. And if you mix the zigs and the zags in different order, the value at the end is still the same. Now, you know something about the sum of the zags is because so there is a result that you can establish quite easily, is that if the sum of the zigs converges somewhere. So basically, if you just take the black segments and put them end to end, and it converges somewhere, then the sum of the zag converges somewhere as well because it's decreasing and we cannot go below 0. And therefore, the sum of the zigs plus the sum of the zag converges. So basically, it means it converges. So this gives sufficient condition for the convergence of the sequence. So if the positive variations, that the zigs, form a convergent sum, UT converges. So I'm going to use that for my step B. But I will need some extra assumptions. Let's come to them. So, I have this constraint that I'm going to say that the square of my gradient is less than A plus B times W minus W stars. But first, I'm going to assume there is no B for simplicity. And I'm going to assume also that sum of the gamma t square converges. And this is going to be enough to prove that HT converges. And the proof is simple. I write my HT plus 1 minus HT plus my zigs. And it's going to be, so the bracket notation with the little plus at the bottom, that means just 0 if it's negative, the value if it's positive. I don't know if I explained that. Well, I'm going to write this. The first term here inside is negative, so there's no impact, so it's less than this. And if gamma, the gradient of C is bounded and the series of the gamma t square converges, well, everything converges. I apply my lemma, and I know that the Lyapunov sequence converges somewhere. I don't know where yet. And when B is different from 0, I have to play a little trick. And that is, unfortunately, in gray, that's too pale. So I define an auxiliary sequence mut A, which is the product of 1 minus gamma I square B. And we can show that it converges somewhere because gamma I square converges. It's something we've done before. And then you define H prime T as HT over mu T. You replace, and that suppresses the B. And then you saw that H prime T converges, therefore HT converges. That's just a technical detail. Now I go to my step C. And I'm going to need an additional assumption, which is that the sum of the gamma T diverges. And that's the assumption that says that the steps do not decrease so fast that you stop somewhere in the process. So you just write HT plus 1 minus HT, which is by the same thing as usual. And both the blue terms are convergent sums. This one is convergent because gamma t square is a convergent series and the gradients are assumed to be bounded. And this one is convergent because we know that HT converges. Therefore, this one is convergent as well, because the difference of two convergent series is going to be a convergent series. Therefore, W minus W star gradient of C goes to 0. And because of the general convexity hypothesis, that means that W goes to W star. We're done with the batch gradient. So you see that as soon as you start to have discrete steps and gains, things become a little bit more complicated. You need to have assumptions about the gains. So there are two here, that the sum of the square of the gains is convergent, and the sum of the gains is divergent, diverges. And you need to have some boundedness condition on the gradient, which was this one. Now let's go to stochastic gradient. Yes?
Sorry, this might be a naive question. Why is it that if gamma t goes to infinity, that second term converges?
Oh no, the second term converges because we already have assumed that gamma t square converges. Then when you know that these two sums, the sums of the two blue terms are convergent, you know that the sum of the black term converges as well.
And the gamma squared converges even though gamma goes to infinity?
Sorry, can you repeat?
I'm sorry, the third term.
The third term, you assume the gradients are bounded, and you assume that gamma t square converges. Therefore, that converges. Then the black one has to converge, but because inside you have the gamma t that would diverge by itself, that means that the W minus W star gradient of C must pull it down. So it has to converge to 0. OK, so let's go to the stochastic gradient. So this time we have Wt plus 1 equal Wt minus gamma t, the j of ZTW, t, which is the stochastic terms. And we define the Lyapunov process this time. This time it's a stochastic process. It's not a sequence. So what you see that we're just changing the tools. For the continuous case, we have a function. And the tool is just the convergence of a decreasing sequence. For the batch gradient, we have a sequence, a Lyapunov sequence, and the tool is this bounded Ziggs theorem's convergence. And here we define a Lyapunov process, and the tool is going to be called a quasi-martingale. So consider a stochastic process ut, and I have a notation that this p of t, well, there is a technical thing that goes with it that can be very complicated, but it's enough to understand that it represents everything that is known on time t. So all the u0 to ut, all the x to t minus 1, and so on. And what I'm going to define is I'm going to define the delta t, which is going to be 1 if the expectation of ut plus 1 given the past is greater than ut. So basically, if at a given step my process has more chance to go up than down, this is 1. Otherwise, it's 0. And the reason for this is that because you have a lot of noise in the stochastic gradient, sometimes the cost is going to go up. And your question is to show that even if the cost sometimes goes up, it's no big deal. It's not going to kill you. So this is something that isolates the indices in time, where the expectation given the past of my Lyapunov process is going that it wants to go up. And the equivalent of the sum of the Ziggs is going to be the sum of the positive expectations. So I take this indices where the expectation that is going up is positive. I multiply by the Ziggs term, and I take the expectation of that over all time sequences. That looks a bit contrived, but there is a theorem that's the positive quasi-martingale convergence theorem. Sometimes, actually, the quasi-martingale is the way that it was called in the French literature in the 80s. And in the English literature, it's called a sub-martingale nowadays. So, OK, it's detailed. So anyway, if ut is positive and this series, this sum, converges, then you can show that ut converges almost surely. So I'm not going to prove this because this is well beyond what can be done in a 1 hour of lecture. I'm just going to use it. So I go to my step B, convergence of the Lyapunov process. So I'm going to have the same additional assumptions, a little bit changed in structure. The first one is sum of gamma t squared converges, it's about the same. The second one is that the expectation of my gradient, my local gradient squared, so basically it's a second moment, is bounded. But the difference compared to what I had is that I cannot say it's just bounded by W minus, I have to say that there is a A. And the proof, I'm going to first do it assuming B equals 0, is exactly the same. You just write the difference. Let me just, you write the difference, ht plus 1 minus ht given the past. So you have to do to pass the expectations. You find here the one where we assume that this is equal to the gradient of C. And this one is, well, the only thing that's changing here is the example that I'm using. So I have this second moment of the gradient. This is supposed to be negative. So it's less than that. So therefore, it converges. Now, if I take just the terms with positive increases, well, I say that expectation of the positive increase indicator, the difference, is the expectation of the positive indicator, expectation of the difference given PT, and you can just shuffle the expectation around, and you get this less than gamma t squared A as well. You apply the quasi-martingale convergence theorem, and you show that, at least in the case B equals 0, the process HT converges somewhere with probability 1. Almost surely, and with probability 1 is the same thing. Now, the case B different from 0 can be done exactly the same way as the batch gradient. You have just to redefine the series, and it's just a pen, not worth showing. And finally, we want to show that it converges almost surely to 0. And I will use the same additional assumption that the sum of the gamma t diverges, and the proof is exactly the same. The expectation of the increase of the Lyapunov is, I just write it this way, both blue terms have convergent sums, therefore the black term must converge. So that means that limit inf of WT minus W star gradient equals 0, otherwise we would have a problem, and that implies the convergence. Because the only way this product can approach 0 is if you come close to the minimum because of the convexity assumption. So, okay, what do I have so far? What I've shown is that you can prove, there is a very well-oiled machinery to prove that this kind of things converge. It's not that different from the batch gradient. The only thing you have to do is make sure that this noise variation, that sometimes because of the random noise, the cost is going to go up, that this going up is not going to kill the convergence. And you do it using this tool, which is the martingale, the quasi-martingale or sub-martingale convergence theorem. The steps of the proofs, they're remarkably the same in all three kinds of proofs: the continuous proof, the discrete time batch proof, and the stochastic proof. It's just that the tool you use, they change a little bit. So now I'm going to the non-convex case. And why should we worry about non-convex objective why should we worry about non-convex objective function in machine learning? Well, it turns out that the life is non-convex. If I give examples, multi-layer networks are non-convex. Clustering is non-convex. If you want to learn features, not just use a set of predefined features, but learn them and adjust them, that's going to be non-convex. If you want to do semi-supervised learning, it's going to be non-convex except in pathological cases. If you want to do mixture models, it's going non-convex. If you want to do hidden Markov models, it's going to be non-convex. If you want to do feature selection, most of them are going to be non-convex. If you want to do transfer learning, it's going to be non-convex. So we have to live with it. And it's true that the theory for convex optimization is a lot more developed than the non-convex one, but the problems we want to deal with and the ambitions we have force us to deal with non-convex problem. And non-convexity comes with a lot of issues. You might have several local minima. You might have several global minima. You can have critical subspaces, so you have a cost function that's doing something very weird, and on the ridges of the mountains, things happen, and on the ridges of the ravines, things happen. You can have saddle points, so you have to deal with that. So what can we say? First of all, in the majority of machine learning problems, what you can have is you can confine the solution to a smaller space. You might have a non-convex function that does very strange things at the bottom, but if you look at it from very far away, it's sort of convex. So basically, the weights are going to be in a certain zone, and you know that they're not going to go out of this zone. And that's very important because you've seen that in all the proofs of convergence of the gradient, we need this boundedness hypothesis on the gradient, for instance, or that we don't go too far. So the first question is, can we stay confined in a certain area? So the way it's done in the classical optimization literature for non-convex function is to partition the space into attraction basins. And you make sure that your W stays in its attraction basin, and you write a Lyapunov function inside the basin, and you go on. And there is Krasovsky in the 60s did that, and things like that. For batch gradient, you can do that quite well, because you're not going to hop from one to the next. But for stochastic gradient, it doesn't work too well, and actually it's a bad idea, because you have this noise. What's happening is that if you have a local minimum that's not too good and not too large, and a local minimum that's much better where you want to go, and you're stuck in that one, you have enough noise that you have a little chance to go into that one. And if you go in the deep one, you have a lesser probability to go out. You can actually analyze that with simulated annealing kind of arguments, basically. So in the stochastic gradient case, you don't want to assume that you have perfect confinement. So you have to do something else. So the something else is going to take the cost function itself as a Lyapunov function. So you suppose that the cost function is bounded from below. There is a C star. And you're going to take CW minus C star and try to show what's going on. So we're going to say that the cost function is positive. It has continuous second derivatives, the standard conditions on the learning rate, the standard condition on the boundedness of the gradient. And we go. And here we have the two global confinement assumptions. So I'm going to show what they mean. So we say that we have two big circles. We have a circle of diameter d and another one of diameter e that's bigger. And we're going to say that inside the d circle, the large circle, the sum of the square of the gradient is bounded, which is not too difficult in general. You know, if it has a reasonable expression, you can say that if you take you restrict the way the weights can grow, you force the weights to be bounded, the gradients are bounded. It comes usually quite naturally. And then we're going to say that if you're outside the small circle, you have something that looks like the general convexity. So basically, when you're outside that circle, the gradient points you in the right direction. And so what we're trying to do is to say that if you look well above, far away from these two circles, what you have is something that looks convex. So these are my two circles. It looks convex here. At the bottom, you can have very strange things happening. And the way we're going to show that, what we're going to show that if you have this assumption, now the probability that WT square is within 2 times this E circle is 1. So that means that you're going to be, starting to some point, you're going to be almost sure with probability 1, that your weights are going to be confined in a domain that's finite and compact and nice and everything. And the proof sketch is, well, just the same. You define a Lyapunov function which is max of E and WT square. You perform the step A, B, C. You see that HT goes to 0, and therefore the WT square cannot go far beyond E. And the thing that now we are working in a set that's compact, WT square less than E, and the continuity implies that all continuous quantities are bounded, which is very convenient. Now we can say that all the things will, yes? Oh, okay, sure. So now we can say that everything that, because we confine in a compact domain, and with probability 1, everything that's continuous is bounded, and it's going to be useful. And now we can say that under the same conditions, the cost converges to some value, and the gradient of the cost goes to 0, meaning that you go to a point that's a particular point for the gradient. You go to some external point. And the sketch of the proof is you define a Lyapunov process, which is ST equals C of WT, step A. Step B, the Lyapunov process converges somewhere. Step C, define a secondary Lyapunov process, which is the square of the gradient. Do A, B, C, and then you show these two things. That C converges, and the gradient of C goes to 0. And for this, you need bounds on the Hessian, so you need some kind of global confinement that's useful. So what does it mean? So it means that you're going to go to one of these points. You can go to a local minimum, a local maximum, or a saddle point, a better minimum, or to a plateau very far away. So the plateau very far away, it's removed by the local confinement, if you have it. You have, and the saddle point of the local maximum, they in general remove because you have noise. So you cannot stay, in extreme case, in pathological case, if you have just one example, you can be stuck on the maximum because it's the same as you're just there and that's it, the gradient is 0. But if you have a lot of examples and some noise, you're not going to stay there. One of the examples is going to take you off the maximum, and then you're going to have gradient, you're going to go somewhere. And these ones can be very bad. So it's good to have the local confinement to make sure that your cost when you go far away brings you back towards the center. And most of the regularization terms do that, actually. So what did we prove now? We proved under reasonably mild assumptions that if you apply stochastic gradient to a non-convex function, you're going to go through a local minimum. And you can refine these proofs and show that you have quite a good chance to go to a reasonably good one, because if you cannot get stuck in a bad one. At some point, you have a chance to get out of it. And now, we're going to look at the second order stochastic gradient descent. So this time, I replace the gain by a matrix gain, gamma t. So in the past discussion, I was often assumed something of the form 1 over t bt, but gamma t can be just that. So this gain is a positive definite matrix, and the idea is that we would like this to be close to 1 over t, the inverse of the Hessian. But in fact, you can have convergence with much weaker assumptions. So suppose that you have a bracket of the eigenvalues of this gamma t that I'm going to call lambda t mean and lambda t max. If you have that the sum of the lambda t mean diverges, and the sum of the lambda t max squared, there is a square missing? Yes, there is a square missing here. Good. So lambda t max squared converges, and the standard assumptions, pretty much, then you get the convergence. So you just need to have your gain matrix to have a spectrum that satisfies the same conditions as the conditions on the gain. And the proof sketch is exactly the same. You're going to take the cost as a Lyapunov function. So you define the Lyapunov process. B, it converges. You define the gradient process. Do A, B, C again. It converges, and you're pretty OK. The interesting thing is that we didn't say anything about gamma t. And when you have this second order process, usually you have at the same time something that's going to estimate the gain matrix to be close to the inverse of the Hessian divided by t. And this something can be complex. We don't care how complex this thing is. It's just sufficient to make sure that the bounds of the eigenvalues of the gamma t remain within bounds, and that these bounds go like the usual learning rates. So that means that you can come out with your second order algorithm. You prefer the way of computing the gamma t and everything, and under mild conditions, you can be sure it's going to converge. Doesn't mean it's going to be that fast, but at least you don't have this issue. So my conclusion here is that there is this very well-oiled machinery. We can establish the convergence of stochastic gradient algorithm under mild conditions in pretty much all situations that matter. And that apply to Adaline, multilinear networks, perceptron, k-means, LVQ2, lasso, and you can add more, and whatever second order algorithm you prefer. They're all the same. Okay, I understand this was a bit, that's probably the toughest lecture. If you have questions, I'll be glad to answer. Yeah? Okay, the speed of the convergence. So under such mild assumptions, it's very difficult to get an estimate of the speed. I did it in previous lectures for the speed in the one-dimensional case, where I could have an estimate of the speed, and for the speed under stronger differentiability conditions with a scaled gradient. So I already gave some examples for estimating the speed. When used first order or second order, we know that second order is faster in terms of number of iterations. And we even know that if you do the correct second order gradient descent algorithm, you're in a situation where after just one go over the shuffled examples, you're as good as if you had the empirical optimum in terms of the testing error. Now the problem is that doing the second order stochastic gradient is expensive because you have to multiply the gradient by a matrix. So instead of paying a cost that's a dimension, at each iteration, you pay a cost that's d squared. So you have two ways to go. Limited storage approximation of the Hessian, where the cost becomes d times k, where k is the rank of the approximation. But then you better make sure that you gain at least a factor k in the number of iterations. And the other one is the average stochastic gradient, which has an asymptotic property that it's going to converge as fast as the second order. Does that answer the question? Okay. Yes?
So I was trying to understand this diagram. Is the assumption that there's these two circles around each local minimum, or is there
No, these are very large circles. So basically, I say that on the large scale, my function looks convex. At the bottom, it can do things that are weird.
Okay, so within the inner circle are a bunch of local minimums?
Yeah, this is where we have all the working the working business. Yeah, all the messy stuff is in there. But if you look at something like k-means, this is pretty much what's happening. When the W are going far away from the cloud of points, the cost increases completely. It's only when the centroids are within the points that you have all these non-convexity effects. And if you look at something like a multi-layer perceptron, there is something that's well known is that if you put a sigmoid on the exit layer and the desired values are on the asymptotes of the sigmoid, you're going to have a lot of problems. So you put them a little bit inside usually. And that means that at a certain distance, you have a nice going up. So that these are all tricks that bring back things inside the zone where that basically create a confinement. If you have a regularization function, something like a term that's lambda over 2w squared, that's also something that brings you back, because in the distance, this term is likely to win, especially if you have the kind of nonlinearities we consider where you have flat zones in the distance.
So the assumption would be, I guess, there's no symmetries that would put solutions kind of at extreme points.
Solution in extreme points are very bad for us because if you have a flat zone in a very distant space, so basically you go that direction, things becomes completely flat ad infinitum, like the landscape around here. Well, the problem is that you have a very large space and decreasing gradients. So you step in the infinity. You go nowhere. Yes?
Will the stochastic gradient give you the sparse solution?
The sparse solution. I didn't discuss the sparsity, and it's a topic all by itself. What I just said is that the cost function is going either to approach the optimum, or the gradient of the cost function is going to go to 0. If you take the case of the lasso, so I had it somewhere. Yeah, let's look at the lasso. It's actually an interesting thing to look at. No, too early. Lasso, yes. So here I'm using this trick, and there is, yeah, it's a whole trick actually, of splitting the W in the difference of two positive terms. So the first coefficient of W becomes U1 minus V1, and the last one UD minus VT, and both are supposed to be positive. So that way I can rewrite the L1 regularization relatively easily, and bring my gradient. I just have to make sure I stay positive. So I project in the positive space. Now what's going to happen is still that this UI and VI, they can move quite a lot. So you have quite a lot of noise there. So at any moment, you're going to have a set of UI or VIs that are going to be non-zero just because the last example you've seen took you away from there. So you lose sparsity by doing this. So you have a very strange situation where if you compare to the batch solution, for instance, and you do stochastic gradient for a certain time, you're very close in terms of objective function, but you don't have the same sparsity. You pay for the noise. So there are algorithms. There is an algorithm by Ling Xiao, which is a dual averaging method that does a little bit better in that respect. And it has some nice results. I can give you a pointer if you want. But this is not really designed to enforce sparsity. Sparsity is a bit of opposite of noise. You know? If you add noise on a 0, you get something that's not a 0.
So like the coordinate descent method will give you a sparse solution using so coordinate.
The coordinate ascent method can give you sparse solutions in the dual space. You see coordinate ascent methods.
Right. If it's a different type of.
Yes, but it's not stochastic. So if you want to do a coordinate ascent, you need to know for each coordinate in which direction to go. And therefore, you need to sum over all examples. And that's what we try to avoid. If you have 1 billion examples, summing over the billion examples to get an idea of where to go for a particular coordinate is tough. Now, the gain of stochastic gradient is that at each iteration, you don't have to go over all the examples. You just take one. So you gain from the very beginning a factor n, where n is the number of examples. If n is large, it's huge. Now, the price you pay is noise. So you can do plenty of optimization algorithms that are going to look at all examples and have an accurate gradient, and you can do standard optimization. But you lose this factor n from the beginning. Now, since we can show that we don't need to optimize completely, we just need to optimize to a level to basically bring the cost within a distance of within a certain accuracy from the optimum that's comparable to the difference between training error and testing error, which is not very far compared to what optimization algorithms do. Typically, you're going to be always in the situation where the gain that you have at the beginning of the stochastic algorithm is going to help you, and that the noise is going to be a problem much later. So that was the point of the argument about the wall slide.
But if the sparsity is required,
there is this Link-Xiao algorithm, that's a stochastic dual averaging algorithm, that, to my knowledge, is the one that gives you the sparsest solution that controls the noise in the best way. But it's still a little bit noisy.
There's truncated gradient.
Which, yes, but you're going to pay for that elsewhere. This is not that different. This has a truncation that's built in the other way, so it's going to be sort of okay. This is already better because you could do, instead of doing this, separating W in two terms, you could just go straight minimizing a W and overshoot and project back. So you can take the gradient of this W, L1 term, and say, well, there is a case where the gradient is not known is when I'm on the hinge, but because of my general convergence theorem, this is going to converge. But this is not going to be sparse at all. But already doing this half truncation, you get already a lot more sparsity, but it's not perfect. And the dual averaging method is basically that you move the truncation in the gradient space somehow. You do an averaging in the gradient space, so it's sort of like the average stochastic gradient, but you average the gradients from the beginning together with the proximal constraints. So, well, I didn't introduce enough things to explain that stuff. But you get a little bit more sparsity empirically. But you might converge a little bit slower. It's more like 1 over square root of t instead of 1 over t in terms of the cost. So it depends what you want. Maybe I should take my Vapnik hat because I worked a lot with him. And sparsity is related to explainability. If you have a sparse solution, it's a solution that maybe you can explain. You can start to comment it because if you have something that's not sparse, it depends on everything, it's very hard to explain. And experience proves that you have to choose. If you want a solution that has a nice explanation, it's not going to perform as well for many problems, actually. It's not true in physics, but if you look in biology or if you look in social sciences or if you look in pattern recognition, it's often like that. So there is the same phenomenon at work there somehow. If you want to converge quickly in the cost function, you're not going to be that sparse. But if you want sparsity, you can have it at the expense of converging a little bit more slowly. That's a bit strange. It's not something that's clear, and having a clear understanding of this would actually be a great progress. Yes?
You said that you didn't show anything about gamma in case of second-order methods. But second-order methods, as I understand, they provide you with step size with gamma, right?
Yes, but you have to, when you build an algorithm that's a second-order algorithm, you have to define how you're going to estimate your gamma t matrices.
Well, the thing is, if you take the gamma equal to 1, because second-order methods, they give you...
Yeah, but let's look at the thing, because 91. Okay, well, talk. No, it's further away. No, it's before. Yes. So see, here I assume gamma t is a matrix. It could be a little gamma t, that would be 1 over t in that case, times a matrix that's more constant, that goes to the inverse of the Hessian. Now, if you write a second-order stochastic gradient algorithm, you have to also describe how you compute that matrix. And that's usually complicated. It's one of the difficult parts of the second-order algorithms. What this result shows that you don't care how you do it. As long as the way you define your gamma t in your algorithm ensures that its eigenvalues are going to have the right convergence properties, then you converge. End of the story. So you the scaled stochastic gradient, where you have a matrix gain instead of scalar gain, converges under very mild conditions. So you don't need to discuss at length whether your second-order stochastic gradient algorithm is going to converge. Chances are that it's going to converge just from general results. And then you can discuss the speed without this annoyance of having to prove that it converges first. Oh, yes.
particular gamma t? And
Oh,
also
yes.
depends if you will stick the little gamma t
Yeah.
over there, which also will affect.
Yeah, but here I just put it inside the gamma t just for simplicity. So this gamma t matrix could be the little gamma t times a bt scaling matrix, and then you can discuss them separately. I'm just telling you that if the complex of the little gamma t and the bt satisfy proper eigenvalue conditions, for instance, the eigenvalues of bt are bounded and gamma t has the usual convergence properties, you're fine. It converges. Then you can discuss the speed. So algorithms like the online limited storage BFGS, for instance, they fall in that category. So as long as you make sure that the scaling matrix has a bounded eigenspectrum, you're fine, it converges. Then you can start to work on the speed. That's a convenient result. So the goal of all this work was to show that we have convergence under very mild conditions. That include that the J term, the update, can be non-differentiable in some points. That includes the fact that the gain can have very weird expressions. But it's not an issue. So what do you think about a 5-minute break? And then the next hour is going to be quite different, less theoretical. It's going to be about imbalanced data sets and Niemann-Persson classification. Thank you.